Well, hello and welcome everyone to my YouTube channel. My name is Mr. Robinson. I am your host as always, and it is an honor and a privilege to have you as a part of my viewing audience here. We are looking at Algebra 1. We're going to have a little question and answer discussion here on week number 7 and 8 that's featuring polynomials. Now here are the 10 questions that were being asked, and I'm going to answer them in this order. And I might throw in a couple of examples along the way. I hope these videos aren't very long in general. You know, this is the first one that I'm doing here, and I hope that it's the first of very many to come. So how do you get an answer, how do you get a question asked on here? Well, it's quite simple. First of all, you have to submit an assignment sheet here every 2 weeks, and the question has to be asked down here. Now, you can ask 1 to 3 questions as always. And of course, you get scored on kind of the question that you ask. The question must relate to topics in the weeks that are being covered. Now, I will be the personal judge as to whether or not I am going to take a question for the choosing, and it's just depending on the material itself. It has nothing to do with the person asking it. I'll select 10 questions out of the I don't know how many, like 80 of you or so that I feel are the best to be answered for the masses. That being said, I had 14 or so that I wanted to answer. I was able to merge 2 of them, and 2 other ones sounded kind of the same. So, you know, I kind of got as many as I did want there. Those who do get their question selected will receive a 6 out of 5 on their question for that 2-week period. So the question's out of 5 points, and you can get that bonus extra credit point for getting asked on here. So of course, always ask away after the end of your 2 weeks and hope that it gets asked on here as well, and then I'll go ahead and answer it. All right, without further ado, let's go ahead and get started. And we're starting with question number 1. And this question says, when determining the degree of a polynomial, do you add all the exponents together, or do you just say that biggest exponent? So, you know, the way that this question was asked, I want to make sure that I can clarify what it's really saying here. First of all, we are referring to degree. And degree has everything to do with exponents, especially with your variables. So the question is asking really about, let's say we have a polynomial here that says 2x to the 4th plus 3x squared y cubed, or something like that. And here's just a polynomial, and they're asking, well, how do you say, first of all, the degree of the polynomial? And second of all, is the degree determined based on the largest looking exponent, or in general, the largest degree? So this is a great question because as we look at this right here, when we talk about writing answers in standard form, we want them to be appearing in descending order of degree. And the degree of every term is dependent on the sum of the exponents of your variables in that term. So for example, this term right here, 2x to the 4th power, this x is being raised to the 4th power, so the degree here is 4. And this one right here has an x squared and a y cubed. And what we're going to do is add those 2 values there, and that will be of degree 5. So although this x has a larger exponent than this x, the degree of the overall term is not any larger than the degree of this term. In fact, this one's larger. So when it comes to writing these in descending order of degree, we should write the 3x squared y cubed before the 2x to the 4th power. That would be in descending order of degree because this has degree 5 and this is degree 4. Now the polynomial, and this is based on another question that was asked, and I want to answer this as well. The polynomial's degree, in this case, is 5. The degree is dependent on the largest, the term with the largest degree. So the leading term here, when written in standard form, has a degree of 5. Therefore, the polynomial has a degree of 5 as well. So do you add all the exponents together? That's one of 2 questions here. Number 1, to state the degree of the polynomial, do we add these exponents with this exponent? No, you just add the exponents in the largest degree. And you already did that beforehand when you determined what order they should be written in. Once you determine the order, now you should already have that number. That degree is 5. And the second question is, when determining the degree, do you just say the biggest exponent in general? No, not just the biggest exponent, but the term with the most exponents in general. Okay, so that's that question there. All right, question number 2. How do you know when to combine like terms? Well, that's a very good looking question here. Let's go ahead and answer that. Now, combining like terms has everything to do with addition or subtraction of terms. And when they fuse together, such as 2x plus 3x right here, what we do is we add the coefficients and we get 5x. Now, what that says is if we have two multiples of x, that is x plus x, excuse me, that's two pluses, x plus x, and we have another three x's, multiples of x's added together, that's a total of 5, obviously 5 x's added together. So you get 5x right there. Now, how come these ones combined? Well, because this is a certain number of x's, and this number out in front has everything to do with how many of that variable is being added. And that's really all that that thing means. So if I have something like 2x plus 3xy, the question might become, do we add these? Do we get 5xy? Well, the answer is based on what's really being added. We have an x plus an x plus xy plus xy plus xy. Now, 5xy says xy plus xy plus xy plus xy plus xy. So are those two things equal? Well, no, they're not equal because this is 5 different xy's added together, whereas there are 2 x's here, and then there are 3 xy's right here. There aren't 5 y's added together here the same way that they're added here. Now, even if there was an extra plus y, that wouldn't quite be the same because that's 2 x's, 3 xy's, and then 2 y's right there. And the difference between these things is that this is x times y added together, right? These are multiples of these values. These are sums right here. This is x plus y. This is x times y. There's a difference between the two. So how do you know when to combine like terms? Does it just have to do with the variables? Well, sort of. If the variables don't match for every term, then they can't add. So for instance here, obviously it's not true. This may have an x like this does, but this one has a y. Excuse me, this one has a y and this one does not. So you wouldn't combine those things. Now, if this thing said 2xy plus 3yx, would those combine? Yes, they would, because x times y and y times x are the same thing. I prefer writing them in alphabetical order just to keep things consistent. So that's the first thing. The variables have to match up. The variables have to match up. Your terms have to have matching variables. Now, the next thing you need to make sure is that the degrees of the variables match. Now, if we look at 2xy squared plus 3x squared y, these also do not combine to anything like 5x squared y squared, anything like that. No, because these variables don't have matching degrees. Remember when we talked about 2x plus 3xy right here? Okay? The reason why these didn't line up is because the products of the variables are not the same. This is x and this is x times y. Well, this thing is x times y, and this is x times y. These products also do not match here. So you do not add and combine these for the exact same reason that you wouldn't here, because technically the variables don't match. You don't have the same products here in the end because of the different degrees. So these would not add. But if you had something like 2xy squared plus 3xy squared, now the 3xy squared, now these are like terms. This is 5 total xy squareds that are adding with each other. So yes, those would equal each other in that case there. So the variables have to match, and their degrees have to match in order to combine like terms. Now that is for addition and subtraction. That's a very good question. Thank you for asking. Question number 3 asks, how do you know when and when not to distribute? And I think the general question, I think the reason this question came up is because one of the first sections that we really looked at was something like if we'd be adding or subtracting polynomials. And they'd be expressed in parentheses. Maybe it says x plus 4 minus x squared plus 3x minus 7. Something like that, and we evaluated. And the tricky appearance of this thing, now this was before we did any distribution of quantities. The tricky thing about this thing here is that you have parentheses, and you're kind of asking, what are the parentheses doing here? I think the main reason beyond anything else is they're just showing them as two different quantities. We're taking a linear binomial with a quadratic trinomial, and you're doing one minus the other. And really, It has nothing to do with anything else except for when it comes to this subtraction here. But this x plus 4 in parentheses doesn't really do anything. That's just an x plus 4. If there's nothing on the outside of it and there's nothing to do inside of it, then you should just write it as is without parentheses. This one, on the other hand, has a negative that you're subtracting the entire quantity. And if these terms can't combine, then each term has to be subtracted. So we're going to subtract an x squared. We are going to subtract a 3x. And subtracting a negative 7 means we're going to add them. And we get a final answer here. If I write it in standard form just to figure this thing out, we get plus 11. Now, there was distribution involved of the negative, of the minus sign, to assign these to become the opposite sign of what they were. It was that kind of distribution. It wasn't the true kind that I think you're asking about. The question really is, so the answer to this part right here is I didn't technically do the distribution that you're talking about. When and when not to distribute like this. This is the question that's being asked. What if instead it says x plus 4, and in parentheses here it says x squared plus 3x minus 7? Well, the difference between this problem and this problem here is obviously the minus sign. Now, there's no operation that's showing up in between these two things. That means that it is multiplication. And in multiplication, and we're going to talk about distribution more than just this problem, so I'm probably not going to solve the entire thing. But in multiplication here, when you distribute, you multiply each term in one quantity with every term in the other quantity. So the x in this quantity will multiply with x squared, 3x, and negative 7. And the 4 will multiply with x squared, 3x, and negative 7. And then you'll add those all up together, combine like terms. That will be a different answer than this. So to answer the question, how do you know when and when not to distribute? Distribution has to do with multiplication. Distribution has to do with multiplication. And when it comes to that idea for multiplication, you need to understand that it's multiplying a quantity with another quantity here. I'm multiplying x plus 4 with this. You see parentheses here, so when you go back to problems like these, you might be inclined to just distribute automatically here. Well, these aren't multiplying, so you don't distribute here. X doesn't multiply with x squared. This is subtracting with this. So the only distribution that's happening is applying the negative to all these, but nothing multiplies with those right here. Just a negative 1 times these, and then all you get are opposite versions of what there are. So that is not classic distribution as what you're thinking about when you talk about distributing polynomials. So let's go ahead and clean this up a little bit. I'm going to give some general cases now, including the ones that we just talked about there. So if you have, let's say, a quantity multiplied with another quantity here, then yes, there will be distribution. You are going to take this a, multiply it with c and d, and this b and multiply it with c and d. Likewise, an even shortened version, if you have a times b plus c right here, there's also distribution because this item on the outside is multiplying with the values on the inside. So those are to distribute. Would you distribute if you had this plus this or minus? No, this would not be distribution anymore. You'll distribute the negative, but you don't multiply these values with these values. Again, when I say distribution, I'm referring to the more quote unquote classic version of distribution. Here's a good one. Do I take something like this and raise it to some power? Do I distribute the exponent like this? The answer is no, you do not. That does not equal a to the c plus b to the c power. That is not a distribution of that exponent there. See, distribution, again, think about multiplication when it comes to distribution, not exponentiation. That being said, when you do something regarding a product inside here, yes, this one does quote-unquote distribute these, but it's not the same idea as distribution there. It's for a completely different cause and purpose. So when in doubt, multiply it out. There we go, that rhymes. When in doubt, multiply it out. If this was squared, you do a plus b times a plus b. Same thing here. If this was squared, you can just do ab times ab, and you should get the same result as what you're looking for here. That should become a squared times b squared for the very fact that there are two a's multiplying and two b's multiplying there. And, so that's the whole idea behind that stuff here. So this is distribution in these senses here. This is not for completely different reasons. How do you know when and when not to distribute? Really, if you're multiplying. Okay, the next question here, question number 4. Are there any other acronyms like FOIL, but for trinomials and so on? Well, that's a good question because, FOIL, which stands for first, outside, inside, and last, FOIL is something called a mnemonic device, and it's hard to spell, but here it is, mnemonic device. A mnemonic device is a clever way of tying in something that you want to recall in things that may be completely unrelated to the subject matter. For example, FOIL. The word FOIL, I guess, is easy enough to remember, and then you use those letters to represent something that you'll be able to recall in a different way. Same as PEMDAS. Now, PEMDAS isn't an actual word, but you probably have heard the sentence, "Please excuse my dear Aunt Sally." And these initials are for parentheses, exponents, multiplication, division, addition, and subtraction, your classic order of operations in these tiers that they're broken down to. Parentheses go first, etc., etc. There's another one for kingdom, phylum, class, order, family, genus, species. Kings play chess on fine green sand. That's for biology. You may hear that one as well. Now, this doesn't spell out a word, but that's a mnemonic device for it. You're going to learn another one later this year for the quadratic formula, where we're going to be able to sing a song for it, and that song is recalled a little better than anything else. Same with the alphabet or anything else. If you know the alphabet because of the song that you sing, maybe that's why you know it. So those are mnemonic devices that you can tie something into something else that may be completely unrelated to the subject matter and all that. That being said, why do we talk about FOIL? Well, to begin with, you have A plus B times C plus D. The first outside, inside, last has to do with A times C multiplying together because they're the first terms in each quantity. Then the outside terms in each quantity, A times D. Then the inside terms in each quantity, B times C. And then the last terms in each quantity, B times D. So you'll have AC plus AD plus BC plus BD. And that's the classic proper distribution of this. FOIL was not invented before polynomial multiplication or distribution. FOIL was an afterthought of saying, hey, let's give training wheels to those who have trouble recalling what to do here or how to make it work. Understand that pattern of what goes on here as you FOIL, as you distribute out, and hopefully over time you'll learn the understanding of distribution. And FOIL does not work for something like trinomials, where you do A plus B plus C times D plus E plus F. If we did FOIL here, the first terms would be A times D. That would be fine. But then the outside terms are A times F. The inside terms are C times D. And the last terms are C times F. And what happens is you totally missed A multiplying with E and B multiplying with all of these. You missed 4 different terms that should have expanded out here. So FOIL doesn't work for something like trinomials, or a binomial with a trinomial, or a monomial with a binomial, or anything like that. It's only for binomials. Now, so they use this thing because it's so common. You multiply binomials so often that it's important to know. So that's what FOILing's there for, but it's not supposed to be an end-all, be-all term. You have to eventually understand what distribution is. Each term in one quantity multiplies with every term in the other quantity. Each term in one quantity multiplies with every term in the other quantity. And that applies to trinomials as well. So when I have my A plus B plus C times D plus E plus F, I should multiply A with D, E, and F, B with D, E, and F, and C with D, E, and F right there. It's hard to kind of draw arrows after that. So is there an acronym for something like that? Well, I think you'd be the first to make one up. That would be kind of hard to come up with, even if you did something where like middle was a letter, like fomoil or something like that. I don't really know. First, outside, middle. It's kind of hard to really state because you got to mention A multiplying with E and B multiplying with all these here. So are there any other acronyms? No, I don't really know if there are any. And at that point, again, FOIL's the training wheels. It's not like they say, are there training wheels for big versions of, say, dirt bike racing or something like that? Well, no, at that point, they don't use training wheels anymore. Instead, they just start to, ride the bike as is with just 2 wheels, and then they keep that kind of balance. So, after FOIL, after you really learn it from the very beginning, then from there, you just kind of understand the idea of polynomial distribution. So I hope that answers that question there regarding FOIL. Okay, question number 5. What is the best way of multiplying 3 or more quantities? Now, they are not referring to trinomials. They could be. The quantities could be trinomials. They're talking about, here's multiplying 2 quantities and equaling whatever, and you can, FOIL, you can distribute, you can do whatever it is that's multiplying here. But what happens when there's a third quantity? What happens when you have 3 and you want to multiply them? Well, I'll tell you what I've never done before. I've never done something like multiply them all 3 at the same time. So I've never done something like if it's a plus b, c plus d, and e plus f. I've never done like, let's do a times c times e, and then a times c times f, and then a times d times e, a times d times f. You can see how hectic that really becomes. That's way too much to do in one step. No, instead, what I'd rather do is just one at a time. So a plus d and c plus d and e plus f. I'd rather just multiply a plus b and c plus d first. Do the distribution that you're supposed to do here by multiplying those out. You end up getting a quantity. Sometimes like terms combined. In this case, when I write this straight out like this, okay, nothing actually combines because I can't really write it that way because they're just letters. But at this point, now I can do another multiplication. Now, there's one thing that I'd also probably do on this stage here, and you probably saw in the last example that I did. Remember when we did polynomial distribution and there was, see how there are 4 terms here and 2 terms here? Well, see, if I start to draw the arrows, and if you're really keen on drawing arrows here, the problem becomes when you want to do extra guys like this, b times bc times this, and you can see where the arrows get kind of cluttered, and that becomes a bit of an issue. So one other thing that I may do in this problem here is I may rearrange the e plus f written first. Because see how much cleaner this looks. There will be still a lot of arrows, just as many, but now you're saying, okay, e is going to multiply with these 4. F is going to multiply with these 4. And you see that they never get in the way of each other. But this is what you'd have to do last when it comes to multiplying these all out. So what's the best way of multiplying 3 or more quantities? 2 at a time. 2 at a time. And, when I multiplied these 4 out right here, what if there were 4 quantities? Well, what you could do, if there is also, what's the next 2 letters, G and H? If there's G plus H here, what I would do is I'd multiply these 2, get what that becomes, and then I'd just multiply these 2 on that same step. So I'm not doing really, literally just these 2 and then a next 2 and whatever. I'll do these 2, and I'll do these 2, and now you have just 2 bigger sets of quantities. Now you have the unfortunate part of a 4x4. You're going to have to do what you can with that. So it's kind of your call on that, but save yourself some time that you don't have to rewrite this and just do the next step as is. So 2 at a time, always. It doesn't matter what kind of quantity it is. I would always do that. I wouldn't ever not. It's a great question, though. Great strategy. Okay, question number 6. This question asks, how do you determine if a polynomial is a perfect square trinomial? It's a good question, and I'm actually not going to explore this fully, but I will just mention, we're going to talk about this a lot more later. First of all, we need to have something that is being squared. So, and the kind of quantity we're referring to is a binomial. When we take a binomial and we square it, the end result will always be a trinomial, and the result of the trinomial will appear as such. The first term will be squared. The middle term here will be double the product of your 2 values, and the last term will be squared. So when we were looking at something like x minus 3 quantity squared, you take the x and square it. You double the product of these 2 values here. Now, x times negative 3 is negative 3x. Double that is negative 6x. And then you take the negative 3 and you square it, and you get 9. So that becomes the appearance of this. And the appearance is, of course, a trinomial. And that trinomial is taking a binomial and squaring it. This is the appearance and form of perfect square trinomial, where you go from one to the other by distribution. Now, if you have trouble kind of recalling that or familiarizing yourself with that pattern or picking it up, I would just expand it out and I would FOIL it, of course. However, the reason that we want to practice this distribution and really recognize this pattern is when it comes to factoring. So how do you determine if a polynomial is a perfect square trinomial? It's already determined for you. The question is, how do you recognize it? You're going to have to get yourself really familiar with not only this idea, but also a bunch of these things together. Let me write out a couple of them to really get you to see the pattern here. X squared plus 2x plus 1. x squared plus 4x plus 4. I'll do x minus 3 squared this time. That was the x squared minus 6x plus 9. Now take a look at what I'm doing with each problem here. The first guy is getting squared. The next guy is double the product of these two. And the third guy is the last guy squared. What's x minus 5 squared going to be? X squared minus 5x doubled minus 10x plus 25, and so on and so forth. This keeps going. So really the idea is play with these enough, and maybe you'll pick up on the pattern of these things here represent perfect square trinomials. That will be important when it comes to factoring these down in a very efficient way and getting these down to here. So here's the overall appearance of perfect square trinomial. We've only practiced going from one way to the other and not really the other way back. What happens when you have a trinomial and you square it? Well, it becomes something much larger than that. It's not just a trinomial anymore when you square it. So that's not a perfect square trinomial. It's a perfect square something else. You don't really talk about those very much at all. This comes up a lot, though. This comes up a lot. Question number 7. I don't understand how to use the zero product property to simplify my equations. Okay, so I did write this question down the exact same way that it was asked, and there's kind of an issue with the wording of it, and I don't know if it's going to bother you as much as it bothers a math teacher, but you know, in terms of simplifying my equations, you don't use you don't use the zero product property to simplify equations. You use them to solve equations. So in terms of solving equations, how do you use the zero product property? First, let me write out the zero product property for you guys here. And I think there's probably another question on zero product property later here. I can't remember, but let's go ahead and write it out. First of all, let's understand the property itself. If you multiply 2 numbers or 3 numbers or 20 numbers, if you multiply a set of numbers and the result is 0, the idea is one of those numbers has to be 0. That's a general math rule. That's besides this algebra and factoring and stuff like that. There's nothing to do with that. There are no 2 or many non-zero numbers that you can multiply and get 0 as a result. They all have to be, one of them has to be 0. And the other part of this rule is as long as one of them is 0, then the whole result is 0. 0 times 1,000 times -4 times infinity, and you square infinity as well. That's infinity times infinity. That result is still 0. 0 times any value, 0. And you know, infinity is not really a value, so I don't really know if I want to say that number. But anyway, you just need 1 0 for it to be 0. So how do you use that property to, let's say, solve my equations? Well, let me do kind of 2 things with this. Let's start off with a problem that's a little bit bigger here, like 2x squared plus 10x equals 0. See, right here, it's hard to solve for x because it's hard to isolate just one of your x's. This is squared. This is not. They can't combine. You don't want to cancel out any x's, but you do want to be able to solve. And this is a sum of values. There's no zero sum property. It's not like as long as one number plus a number is 0, one of them has to be 0. No, that's not even close to true. But it's true for a product. So the real question is, how do you turn this into a product? This has to do with a common factor. If I can divide out something from both terms, like a 2x, I'm left with an x here and a 5 here. That's safe for a later debate. But why did I do this? Because what I've created now was a product. I've created one thing multiplied by another. And the idea is that this becomes like your a and your b here. So if 2x times x plus 5 equals 0, one of these has to be 0 for this solution to be true. See, if this quantity is 0, then 0 times whatever this is becomes 0. Or as long as this is 0, then 0 times whatever this is becomes 0. So what you do is you create, and I do know that this has to do with my next questions a little bit. What you do is you create 2 different equations right here to state the conditions for these scenarios. So x can either be 0 or -5. So that's how you use the property. You search for a product that's set equal to 0. And then you create conditions. You create the conditions, either or, one or the other. And these are much more solvable because you can isolate this x variable, whereas you couldn't in the beginning. So that's how you use it. Now, how do you simplify something? Well, technically, going from factoring to standard form is called simplifying. But how do you go from this to that? As far as you know so far, you're trying to find what's called the greatest common factor. Eventually and later, we're going to be factoring quadratics in other ways that'll be able to let us do distribution even in larger forms, and even be able to do ones like these previous ones that you saw right here. Be able to factor those more largely, and it'll get us kind of the same effect. Okay, question number 8. Now, this is really 2 questions, but they were so much the same that I wanted to answer them under the same umbrella. And it has everything to do with the last question as well, zero product property. Why does one variable allow there to be more than one answer in an equation? That's one question. The other question is, how can the same variable be 2 different answers at once? So, they're kind of the same question here, and to answer both of them, really what we've seen them in is with quadratics. This is a quadratic binomial right here. It's a quadratic polynomial, and where you've seen more than one answer is with quadratics. You've never seen more than one answer in a linear equation, except for one that has literally an infinite number of solutions, in which case all we say is infinite number of solutions, but we can't specify 2x answers. Now, the reason for this really has everything to do with looking at things as graphs here. If I convert sides of an equation, expressions, into graph form, and I graph 2 different things, what if I graph 2 different linear equations, like this one here and this one here? The point of intersection of these 2 can only occur once. Yes, they can occur no times if this is parallel, or an infinite number of times if they're on top of each other like that, but we're just talking about if they're 2 unique equations, they can only intersect once. There's only one way that 2 lines can intersect once, and it's like that. We'll see quadratic equations have different kinds of graph appearances. You might have a quadratic even with a linear equation, or matched equal to 0 or anything like that, and the result of that is a parabola. And we're going to graph these later. It's not a very good looking one, but it's a U shape. And the reason for this is because of the squared quantity. You see, when I square a value, its result becomes positive regardless of what it was before. And when I square a larger value, the difference in squaring a value that's some distance apart from another one is substantially larger. For example, 3 squared, 4 squared, and 5 squared do not have the same distance away from each other. This is plus 7. This is plus 9. And obviously, if I look at something like 100 squared, 200 squared, or 300 squared, the difference between those is not the same either. So there are kind of 2 principles to this, in that number 1, it bows back up or back down, depending on which way you're talking about. And number 2, the increase sharpens more as you go. That's why it becomes a U shape. A better looking parabola would probably be more like this, kind of slants off, and then it comes back up right there. But it starts to increase over time. And when it intersects with another point, it can intersect at 2 different places. Now, I know I'm going kind of above and beyond with that question, but that really is an exploration question in itself. What we're doing is talking about how can there be more than one answer? Because when you square a number, it becomes positive again. Let's look at a very, very basic example here. X squared equals 9. I'm just going to ask you, without doing any mathematical things to this, what numbers can I square to get 9? Well, 3 squared gives you 9. But so does negative 3 squared. So you can already see there are 2 different answers for x here. X can be 3 or negative 3. And that's just the very beginning of your quadratic material there. It's because the fact that as you square a negative number, it can also be the same result as squaring a certain positive number. And that's what you kind of get as a result. That's why there's more than one answer in some of the equations, specifically with quadratics or cubics or whatever else. But we're going to deal a lot with quadratics in these chapters. Now, how can the same variable be 2 different answers at once? The answer is it can't. You say at once. That's not what this thing is. See, when you get x squared equals 9 and x equals 3 or negative 3, there's this word or here. X can equal positive 3 or x can equal negative 3. It can't equal the same 2 things at once. So, consider these problems that we talked about here. Zero products property. We got x equals 0, x equals negative 5. Now, I didn't put the word or in between, but I really should have. But let's look and double check this. Now, as we double check this, x is only going to be one of these 2 numbers at one time. Take, for example, see, you might have thought that it said, oh, let's plug in 0 for x right here, 2 times 0, and let's plug in negative 5 for x right here, negative 5 plus 5. So we get 0 times 0, which gives us 0. Well, that's not untrue that 0 times 0 gives us 0, but we're not plugging in 2 different x's at once. We're just plugging in one of them. Let's say I plug in 0 right here and 0 right here. 2 times 0 is 0. 0 plus 5 is 5, but 0 times 5 is 0. Okay, that's what we're doing. We're plugging in 0 once. Does it matter whether I plug in 1 in one area or both? Or same with negative 5, but does it matter if I plug in both at the same time and stuff? Well, yeah. What if I look up here? 2 times 0 squared plus 10 times negative 5. What if I just chose to plug in one of the numbers, the other number in this place? This would give me an answer of negative 50. Clearly, that's not the case. So I'm not plugging in both x values at once here. I'm doing one at a time, and either case satisfies this condition, not both at the same time. So how can it be two different answers at once? It's not two different answers at once. But if your question is more, why is there allowed to be more than one answer? Again, we talked about that stuff with the quadratic. So kind of two different things at play there when you're asking that question. Question number 9, what's the proper way to check your answer for polynomials? This is a great question. And what I think is really being asked is, as we practice our distribution stuff, x plus 2 times x minus 4. If I want to check and I distribute this, x squared minus 2x minus 8. I hope I did that right. How can I know this is the right answer? What I would do is I would choose any number in the world. I would try and avoid the numbers 0, 1, or 2, only because these can lead to what are called false positives, meaning you could run into this side matching this side, and it possibly is not true just because these numbers have some weird behavior things to them that can allow that to be true, even though it's not necessarily. Try another number like 3. Plug in a number 3 here and see if the left side matches the right side as you do it. So right here, 3 plus 2 is 5. 3 minus 4 is negative 1. On this side, 3 squared is 9. We'll get minus 6, minus 8. 5 times negative 1 is negative 5. This is 3 minus 8, which is negative 5. And that checks out. So every so often, you might run into a false positive with another value like this. But in this case, I think you can just trust that that answer is true. So if you plug in 0, 1, or 2, I think you might run into more false positives than you know. So that's one way to double check. Plug in any number of your choosing, because that's the whole thing about simplifying an expression or multiplying or whatever. This side should equal that side. There should be no difference with when I plug something in. Now, what if you have an equation? What if we have that x equals 0? What if we have 2x squared plus 10x equals 0 and we get these two solutions? How can you know if they work? Well, just like before, you could take these, 0 and negative 5, and plug it into your factored form. I'd really plug it into the original equation. Plug it into the original equation, see if you get that. The other thing that you're really asking about possibly is, how do I know if I factored this correctly? Well, I would go and distribute back out. What is 2x times x? That's 2x squared. What is 2x times 5? That's 10x. So there are a lot of double checking things along the way, and really it has to do with factoring. You know, later down the line for polynomials, we're going to look at polynomial factoring. How do you double check? I would distribute back. I would distribute back and see if I get the same thing back. So those are a lot of different ways to check. So when you ask me, is something right or wrong? Yeah, maybe I'm just doing the problem again like you were, but maybe I'm doing those double checking methods. You can do those for yourselves. Now the real question becomes, if I have the wrong answer, how do I get it right? Well, that's up to you, right? You have to probably go back to the beginning and see where the error was in your ways. I hope your double check didn't give you something wrong. For example, if you used a negative 3 instead of a positive 3, be very careful. Make sure the negative 3 gets squared to become a positive 9, right? It still becomes a positive 9. That's the whole idea about the squaring thing that we talked about before. Okay, and the final question here is question number 10. Why don't we do anything with the exponents when solving for zero product? And I believe the question is being asked as such, like if you have something like x, here, let me start off with a problem, like x cubed plus, let's go, 18x squared plus 81x, and I can factor out an x here, and then I'm left with, I'm going to go and factor this down for you. You might not know all of this, but anyway, so it factors down to that, right? So whether or not you believe it's true, why don't you trust me for it? What you have here is a product of two entities here, but it's not really just two. This guy is being squared. So the question becomes, why don't we do anything with this squared guy here? Well, you sort of can. Let's separate the herd though. This is a product times a product. This is something times something, the result's a product. So this is, if this times this equals 0, either this equals 0 or this equals 0. So x equals 0 is one of your answers. Now we deal with this here. If x plus 9 squared equals 0, what are some things you can do with this square in a more logical sense? Well, one thing you can do is you can expand this thing, call it x plus 9 times x plus 9. And now you have a product, and you say if this times this equals 0, either this equals 0 or this equals 0. But the funny thing about something like this is that this is the same thing twice. When you get x equals negative 9 or x equals negative 9, you got the same answer twice. That just looks a little silly. You wouldn't be marked wrong for writing it twice, but you might get a few eyebrow raises. It's really just x equals negative 9. Now, that is a duplicate answer, and it's said to have what's called a multiplicity of 2, and that has everything to do with this here. But how else can you deal with it? Well, you don't have to write this twice as a product here. You can just ask yourself, well, what value do I have to square to get 0? Well, that's going to be 0. The only way is if this thing inside here was 0. So what did I do with it? I still took care of it. I still thought about what I'd have to do to square to get it. But mathematically, what do you do with it? Well, eventually down the line, you're going to be solving doing this. You know how like when I subtract 9 over here, I'm doing the inverse of addition. I'm doing subtraction. Squares have inverses as well. They're called square roots. I would square root both sides. And guess what the square root of x plus 9 squared is? It's x plus 9. You might have someone tell you it's the absolute value of x plus 9, but I'm going to ignore that for now. And the square root of 0 is 0. So I still get to this step right here. So I do something with it. It's just that why don't we really treat it like anything? Because it's just the same thing multiplied twice. We're already still taking care of that answer in that quantity for 0 product property. And all we need is this inside quantity equals 0. The fact that you have more than one of them doesn't change the fact that your result would be 0 if you plug that thing in. All right, so that'll do it for those questions here. This thing ran a little longer than I probably would have wanted it to. In the end, ultimately, I want to see if I can get these things down to a half hour or something. But I want these questions to be answered, and I want you to absorb this and have some fun with it, and I sure hope you did. So again, that'll do it for this time, and hopefully in 2 weeks, we get another set of 10 questions, and they will be answered for you. Fiend!